in this area and very likely greater than mine. Hello, everyone. Welcome to Concurrency Knowledge Share. I'm going to share my screen. Hopefully there's nothing on my computer that's too embarrassing. Let's close Chrome down. Great. Okay, so we're going to be talking about concurrency. I guess the first thing to say is, for those of you who've been enjoying the talks, and if you want to look at any of these, they are up on, the material is up on GitHub. I'll put the URL in the channel afterwards, and that's the previous 5 talks that I've done in these knowledge shares as well. And there was this PDF and the code examples that I'm going through were posted in the channel as well. So Kelvin asks, what can we hope to achieve in a short space of time talking about this topic? So the things we're going to look at are the basic principles of concurrency on a computer. Concurrency means doing more than one thing at a time. And we're used to being able to run multiple programs and have been for many years. And how do we do multiple things at the same time is often a question in programming. We'll be looking at the global interpreter lock in Python, which is very important when we talk about concurrency. We'll look at async, and specifically async IO, which is very important, particularly within Gigaclear. And then we'll look at threads and processes as different models of concurrency, and some code examples in Python. And we'll talk a very little bit about the future for Python and concurrency. Possibly will surprise you. We'll find out. Okay, so multitasking. And this is where we talk about from AmigaOS to a multi-core world. So for a very long time, especially for consumer computing, which really kicked off in the 80s, and all the way through to the 90s, every computer that you were working with had a single CPU. And it wasn't until AmigaOS, which I think was late 80s, early 90s, and ran on a 7 megahertz 68,000 CPU. This was the first consumer operating system with preemptive multitasking. So the core thing to understand, I guess, is that if you have a single CPU, if you want to do multitasking, if you want to make it look, well, now let's carry on with the AmigaOS, sorry. So before that, Windows 3.0, I think, had cooperative multitasking. And prior to that, we hadn't expected to run more than one app at a time. And cooperative multitasking means that the operating system does things like drawing the windows, reading and writing files, talking on the network. That's all inside the operating system. So there's a whole ton of stuff the operating system has to do. And then you have multiple programs wanting to run. So with cooperative multitasking, one program runs at a time. It will then yield back to the operating system, which will do its housekeeping, and then yield to the next application. So one application has control at a time, but by switching very quickly, it can feel like you've got multiple things running at the same time. The trouble is that a single badly behaved app that doesn't yield correctly can just block everything, the whole operation. And that was the sort of state of the world. And then AmigaOS came along, and it had preemptive multitasking. They used hardware CPU interrupts. So every so often, every few milliseconds or whatever it was, there would be an interrupt. The register and CPU state would be saved, and control would return to the operating system, which could then run its housekeeping tasks. And so we're still running on a single CPU. So in actual fact, at this point, and in these days, there's still only one thing happening at a time, but this switching is happening really fast. The CPU does some stuff and then switches to another app or to another thread or process. The CPU state is restored. So as far as the application is concerned, it's just running smoothly. It doesn't see these interrupts. It's completely invisible. So an app can no longer block multitasking, and you don't get these sort of jerks when using stuff. And that was on a machine largely sold as a gaming machine. But the point is that they were running on a single CPU, so you can have the appearance of multiple things happening at the same time, but actually what's happening is a task is running, there's a context switch, something else runs, there's another context switch, and we go back to the first application. And the thing is, if you take something that's going to take a long time, and you split it up into multiple tasks on a single CPU, you can run them all simultaneously, but there's that context switch cost of storing away the register state and then restoring the state for the next task. And so that context switching means that if you take on a single CPU something and try and run it in multiple threads, perhaps, it's actually going to take longer because of the cost of context switching. And this is perhaps a little bit important to understand when we look at the global interpreter lock and how we got that in Python. Okay, so nowadays, multiple CPUs, each with multiple cores, are the reality, and especially when we're running stuff on servers, have very powerful computers available to us. So modern computers can do parallel processing. They can genuinely run stuff simultaneously without paying the overhead necessarily of task switching. Okay, so that's a little bit of context on concurrency, how we got to the world we're in today. Well, when we're talking about concurrency, we tend to talk about IO-bound tasks or CPU-bound tasks, and there's a very simple little diagram there showing you if you've got an IO-bound task, something that's reading from the network or from the database or from a file or writing to those things, and web apps clearly do a lot of network communication. It's the task itself is going to spend most of its time waiting on I/O because the CPU runs much faster than I/O stuff. A CPU-bound task, something like number crunching, image processing, is something that's going to spend most of its time doing calculations and relatively little time doing I/O or in-system calls. A web crawler or a web server, a web application, typical I/O-bound tasks, image processing, machine learning. Those are classic CPU-bound tasks where you're going to spend most of the time burning CPU. So when we're running code, the basic unit for task execution is a thread of execution. And even if you're not using threads, if you're running Python, you're running code in a thread, probably the main thread. Threads are an operating system level construct, and they're scheduled and managed by the operating system. And Python uses real system threads. So that's going to be P threads on Unix-like systems and real Windows threads under the hood. There is a big kind of gotcha. There's the global interpreter lock, and I'll talk about that in a minute. But Python has real threads, and the thread is the basic unit for concurrent task execution. Alternatively, for running multiple tasks concurrently, you can use multiple processes. When we launch any program, it runs as a process. When you run code with Python, it runs as a process. It runs as a process that has a main thread. Processes are memory isolated from one another. This was a great cause of the downfall of the Amiga, in that the operating system was blazingly fast because you passed pointers everywhere from app to operating system and between apps, and there was no memory isolation. And so then as operating systems developed, we got hardware, memory management, and memory isolation became a standard feature. It was very hard to port AmigaOS because it relied so much on being able to pass pointers everywhere, which meant one process could trample on another. So in a more modern system, processes are isolated from one another. They have an environment, and we can run processes. They're managed by the operating system. We can run those concurrently. Programs can launch sub-processes, and those sub-processes inherit the environment and can even have a modified environment. But the thing about threads is they all run inside the process. So they all have shared access to memory that the process is using, shared access to objects and resources. And this is a cause of great problems with threads, because as soon as you have concurrent access to resources, you can have resource contention, deadlocks and race conditions and all sorts of fun things. So you then need a variety of tools, primitives, and programming techniques to avoid those problems. Processes avoid that by having no shared memory, although in Python 3.11 we do gain some very primitive shared memory resources in the multiprocessing module. So if we want to communicate between processes, and obviously if you're going to take some task processing data and you want to use them and do them in separate processes, we're going to need to pass information and get information back. We need to use inter-process communication. And we have both the subprocessing and multiprocessing modules in Python to do this, and particularly because of the global interpreter lock, but also because of all sorts of problems like race conditions and so on. Use processes, not threads, is a common Python mantra. The global interpreter lock. Up until Python 3.13, Python has a global interpreter lock. That's this, in Python 3.13, that situation is clarifying. The global interpreter lock ensures that only a single thread of Python code executes at any one time within the main interpreter loop. And that fact means that there's locking, there's a lot of locking that just isn't needed inside the interpreter loop and inside the core objects like dictionaries, etc. And Python is as old as Java. It's been around a long time. And single CPU, sorry?
It's older than Java, isn't it?
By a couple of years or something like that. And it depends when you count the first release. Python had a public sort of beta release that was before the Java or something like that. But yeah, they're just about the same age. Although Java has true threading. So, but certainly back in those days, the single CPU was the common case. And so if you split your CPU bound code into multiple Python threads, it was going to run slower anyway. And with IO bound tasks, the fact that only one runs at a time really isn't a problem because most of them are waiting on the network or waiting on their IO. So Python threads are really only suitable for IO bound tasks. If you split CPU bound tasks across threads, they will run slower. There are some caveats. C extensions can release the GIL, so you can have threads running in C code and in Python code simultaneously. But there's only one thread of Python code running at a time. So typically, if you want parallel processing, we say use processes. That's not always suitable. There are a bunch of algorithms that run fine in parallel that require shared memory that you can't efficiently spread across processes and stuff like that. And there's also another model that's suitable for IO bound tasks, and that's async programming. So let's switch to that. If those who've done programming within Gigaclear will probably have done some async programming. It's not true concurrency. Async has an event loop, and when you the event loop is what has control. It runs in the main thread. It has the flow control. You give it tasks. Those tasks can spawn more tasks, and it will fetch data from them. And if there's a new task created, put it to the end of the loop. So I'll explain that much better in the next slide. So tasks are non-blocking coroutines, and the non-blocking is important because Python is only actually executing one thing at a time here with async programming. That's the kind of cleverness of async. And then control goes to the next thing. And because they're IO-bound tasks, async is only suitable for IO-bound. Most of them spend most of their time running on networking on IO, and it feels like they're running simultaneously. So we have the async and await keywords. We use awaits to add a new task to the loop. Async is used for the definitions. And there's an important point here. If you make any blocking calls, you're going to block the whole event loop. So for stuff like reading from files, sockets, creating sockets, all of that stuff are alternative system calls, and that's what the async IO library uses under the hood. So for example, loop equals async IO dot Is it new loop, I think, isn't it? Go away. New event loop, I think. On the next slide. So if we look up the stuff that's available on the event loop, there's a whole bunch of socket-related stuff and communication, networking related stuff, because those are non-blocking system calls. When you make one of these calls, you'll wait on them, and control goes back to the event loop. So here's some very simple code, just demonstrating the synchronous nature of async code. We'll define an async function. That's one that can be waited on. What does this one do? Okay. There we're going to wait on another function. Which is why using idle is great, because I can as I go. Right, and then we're going to have another async function, def other. That's just going to return. Let's do this correctly. Let's have this. 3. Either use loop.run until complete or asyncio.run, run until complete. So I'm going to give the loop a task. I'm going to call function. Now, if we call function, it produces a coroutine object. This is an async function. So we have to use it. We don't call it directly. We use it with the async machinery. So we do loop.run until complete. Put a task into the event loop. It prints 1. We call await. That puts this function call into the event loop. That's called. It returns. Execution returns here. So 1, 2, 3. So even though we're using async IO and the async stuff, code is actually executed synchronously. So if we were doing it like this, there would be no point in using any of the async stuff. However, that's not typically how we use it. Here we've got an async function. It prints 1. It does an async io.sleep. So we sleep and never do time.sleep in your async functions. Time.sleep blocks. Async io yields back to the event loop. So this is the count with an async IO sleep in it. I was just testing this code before. So here's our main function. We're going to gather together 3 tasks, 3 counting tasks, and we're going to run them. We're going to run them and time them as we do it. So we've got 3 of these functions. Each of them sleeps for 2 seconds. Is that right? Something like that. Okay, let's run them and see what happens. 111 printed pretty much straight away. There was a pause, and then we got 222. So what happens in the code is we gather together 3 counts. They go into the event loop in this order. We start executing the first one. It prints 1. Then this code is sleeping. So the event loop can take control, jump to the next one, which prints 1, and then sleeps. So we jump to the next one. So effectively, they're all sleeping together. And then they wake and print 2 all together. So the total time taken, they sleeps for 1 second. The total time taken for executing 3 functions, each of which slept for a second, was just over a second. Cool. So here, all 3 functions are concurrently sleeping. We also have async generators and the async for syntax. Async generators are nice. I used one today, chunking up calls to the property service in batches of 1,000, because we're probably going to have about 1 million, and yielding results, as we call them. This is in the new direct mail project. It will be fun to see how terribly it performs. So that's a very brief overview of async. Async is sequential, all runs in the same thread. You have to use non-blocking code, and we have some interesting constructs around it, and I'm particularly fond of async generators. And the point of using an async generator is you can await inside them, and then you use them in an async for. So threading. When you run Python code, it runs on the main thread. So the interpreter loop is executing bytecode. Here we create another thread, which creates a new thread of execution, and execution now continues concurrently on both threads. That's the basic principle. They happen within the same process and have access to the same shared resources. So you can read the thread yourself. The actor model, CSP, is a great way to maximize sanity when doing concurrency. Because of race conditions, threading can be hard, and being careful around shared resources makes it easier. We use the threading model to access threads and the various primitives like locks, events, and queues. This is how we create a thread. We use the threading module. We instantiate the thread class with a target function, just a normal function. Pass in any args we want that function called with. Then we call start, which creates and starts the new, starts the new thread. But we have control. We have control of the flow. The other thread is running in the background. Let's I can't select one. What time are we doing? Half an hour? If we're doing half an hour, I think I've used an hour in the past, haven't I? Yeah, I scheduled an hour. Okay, let's keep going. We're about halfway through, which is about right for the material. So creating and using threads is as easy as this in Python. It's just a few codes. So here we have a simple countdown function. We have what would be a simple countdown function. It counts down and sleeps for 5 seconds in between. Import threading, import time. So we go, create a new thread. Target is the countdown function, and the args will count down from 10. We pass in a tuple, so that's the syntax for a one-pull tuple with just one member, and we can start the thread. Execution will continue in the background. You see, I still have control flow here. This printing is being done from the background thread. So that's all there is to say about threads. Let's move on to processes. Not true, there's a bunch of more stuff we want to do. How do you know when a thread is done? Whether you can use queues to send things into threads and get things back from threads, or you can use simple objects to communicate, but I don't recommend it. And you can also join a thread which blocks until the thread completes. Threads aren't allowed to join themselves because that would be instant deadlock. So it only works from another thread. So typically you might launch a bunch of worker threads and then join on them all until they're all complete. In pure Python, we cannot terminate a thread. This is a limitation of threading in Python. Other languages allow it. You can do it with C types and an OS level call. Officially, it's not recommended. The normal technique is periodic polling and setting a flag telling the thread to terminate. Yeah, there's a link there to the C-type solution for killing threads. There's a bunch of code examples. I don't know how much time I'm going to have to just read a few of these windows, go through this. This is the simple thread creation example, passing arguments in. Let's run this code. Here we're naming threads. So we've got a couple of threads with the same target, one of them named, one of them not. Let's see if this works. Yeah, so the thread has a name, and there's the current thread API to work out where you are. Current thread, and that gives you a thread object which has a name. Okay, so a big problem that working with threads introduces is the possibility of race conditions. And it comes in places you may not surprise. You have a race condition wherever you have more than one thread accessing and modifying a shared resource. You also have the possibility of deadlocks, live locks, resource contention. Locking is how we avoid race conditions. So what is a race condition? Suppose we've got some code inside a module and it's updating some data. X plus equals 1. We're incrementing a variable. X plus equals 1 is not atomic. It doesn't happen all in one go. It's the exact equivalent of X equals X plus 1. So what happens if we have two threads executing this code at the same time? At the start, for both threads, the execution is moving downwards. And the GIL makes no difference to this, by the way, because the swap between threads can happen at any point. You have the exact same potential problems with race conditions within your own code. So X is 9. They both hit the X plus equals 1 statement at almost exactly the same time. So the first thing they do is read the value of X. Value of X is 9. They both add 1. And then at the same, more or less the same time, one will set the value of X to 10, and the other one will set the value to 10 as well. So we've had two threads, add 1 to 9, and the result is 10. The result should be 11. So what we need to do is lock around the access to X. And so any code that wants to modify X has to acquire the lock, and only one thing can hold the lock at a time. Mutex locks. All access to shared resources should be protected with locking, and that's why getting rid of the global interpreter lock in Python slows down code, although with a lot of work, not as much as you might think. Okay, so we have threads. We need thread-safe ways of communicating with those, between those threads. So we have events, queues, conditions, semaphores. We have thread local variables, etc. And there's some example code. There's an example using logging instead of print statements, because of course print statements aren't thread safe. So even when you're experimenting and messing around, use the logging module. Don't think I need to tell many Gigaclear employees about using logging. We use it a lot. There's thread starting and thread joining, the isAlive API. And so you can ask a thread if it's alive. There's also, when we join threads, we can pass in an optional parameter. This blocks. We can also pass in a number of seconds to wait, I think. And it will tell us whether it succeeded in joining or not. Here's some example code with a lock. We've got a counter. it's got a value that we want to protect to be thread safe. So we create a lock and we protect access to increment the value by holding the lock. It's pretty simple. And you can see there, if you run this code, you can see what it's done. There's a more complicated example as well. And the final example that code that's in there is inheriting from thread and overriding the run. So that was an example there of using a queue. So this is quite a nice pattern that I like. I use it quite often with processes. We're going to have a bunch of workers. We're going to use a queue to manage tasks. So we're going to put those tasks onto the queue. You can pass objects down this queue. So every worker is instantiated with the same queue. We put tasks onto the queue, and then when we're done, we put one none for every worker on the queue. These workers, they're pulling data, I guess, from the queue to process. This is a thread-safe queue, so we can share it between many threads. And when all the work is done, they get the poison pill. They know it's time to go away. This kind of sort of worker pool approach, although there are higher level constructs for it, there's a thread pool, there's a process pool, is particularly important with processing for reasons that I will explain. Okay, it's a really high level overview of showing how to use threads, the principles, and the threading module. I don't think we're going to use it a great deal within Gigaclear. You can use it with Async for pushing background tasks and running background tasks in threads, but that depends somewhat on the framework that you're using. Async and threads play quite well together, so long as you stick to IO-bound tasks. Okay, processes, that's a different level of abstraction for concurrency. And we use the multiprocessing module. The great thing about that is it has a identical, where possible, API and primitives to threading. So you can take code that uses threads and port it to using processes pretty easily. And also, as you learn one, you're kind of learning the other as well. On Linux, multiprocessing uses fork. On Windows, it doesn't. Windows doesn't have fork as such, and Python doesn't use the Windows equivalent for whatever reason, probably for good reason. So on starting a new process with the multiprocessing module, the environment and task are pickled over and sent to the new process. And obviously, pickling is a transmission protocol, a serialization protocol. It takes time. So there's a higher startup cost for processes. So the model I like to do is start up a whole bunch, use queues to send work in, and have these worker processes in a loop processing data, rather than starting a new process per task. So you pay the startup cost once. If we're using processes, we don't have the problem with the global interpreter lock. There's one GIL per process. The inter-process communication, the IPC, typically uses serialization and network calls. So it's a high cost. You do have shared memory access in Python 3.11, but it's very low level. You can use it for sharing bytes arrays and NumPy arrays and that kind of stuff. And just as with threads, the CSP, the actor model, concurrent sequential processing model, is a path of sanity. So the Go and Go routines, they use and implement the actor model very well. And the idea is that when you pass objects in to a task, you pass ownership as well. That's the core of it. So you don't access shared resources, so you avoid a lot of the problems. And if in order to send a result back, the task will send objects back. So typically you have a couple of queues into your tasks or your Go routines, one for sending stuff in and one for fetching stuff back. But you treat it as if it was a separate process. Obviously, using the multiprocessing model, we are separate processes, and the actor model works very well. The API for creating processes, just like creating threads, and the API is the same. Something to be aware of is that when the subprocess is created, particularly on Windows, the target will be imported. This code will be imported in order to find worker. Here we've got a function that's defined. Processes, the worker function is going to be called in each subprocess. Let's have a look at this and run this. Oh, I'm on Windows, so this will be. I can show you what happens if you forget to do this check. So what happens is I'm creating a process with a worker function, and each worker is being called in a separate process. When the process starts, in order to access the worker function, it imports the module. It's not the main module, however, so it gets the worker definition. This means if you forget to do this check, let's just do true. When it imports the worker function, the subprocess will spawn a bunch more subprocesses, and the multiprocessing module will not even let you do it now. That was a very long traceback, though. There we go. In some early versions of Python, that was essentially a fork bomb. You would create a ton of processes until you run out of memory or whatever. Okay, it works by importing the function is executed in a subprocess. That's not very useful unless we can communicate with them. So here's a process that we create with a worker function, and we pass in a queue. This is a multiprocessing.queue, same API as the threading.queue. We start, this is our worker function. It takes a queue, it fetches something from that queue, an object, and it calls a method on that queue. So this is an example of passing objects into a subprocess. So we start the worker in a new process. We instantiate this class, which has a method. We put it in the queue. And that is then pickled and sent across to our child process that fetches it off the queue and calls the method. So do something, prints this message. Doing something fancy in process 1. So you can pass objects backwards and forwards between processes. It's nice. There's also a multiprocessing pool, async result objects. So let's have a look at some of the other code. So here's an example simulating the actor model. So our worker function, it's got a number to identify itself. It's got a task queue and a results queue. It loops fetching things from the task queue. If we get the poison pill, we kill ourselves. Otherwise, we execute the task and put the result. We signal that the task is done, and we put it into the results queue, or put a result into the results queue. So that's the worker. We create a bunch of those, we start them, we put a bunch of jobs. That's the job function that's being sent in to the worker queue. We put 100 of those jobs into the queue, and then we put some poison pills. We join the tasks. This is a joinable queue. So this will block until all the tasks are done. And then we can put, when all the tasks are done, we can pull the results out of the result queue. So what this is going to do is it's going to create a bunch of processes. There are process pools. We're going to create a bunch of processes, start them off, give them a load of work to do, and wait until they're complete. And this is the worker function. And this is the inner loop that is pulling stuff off the queue, executing those tasks, and reporting the results. So let's run the code. What's the number of workers? How many workers we've got? The number of CPU count times 2. How many is that? This thing is reporting that has 12 CPUs. It must be counting hyperthreading. And there we've got a bunch of the workers started, the workers completed all the tasks, they shut down, then we printed the results. We could have printed the results as they were coming in. It's just not the way it was done. So we split 100 tasks between 24 worker processes. Any questions?
Yeah, is that easy to produce some, daemon processes during that last example?
Oh, we didn't talk about daemon threads either. So again, is it possible to access the processes as processes? Yeah, they're normal operating system processes, and when you create this object, it has a bunch of metadata on it and stuff on it. If you just want to interact with sub-processes, the sub-process module is actually really good, and you can set up the standard in, standard error, standard out streams and communicate with your sub-process. The nice thing about multiprocessing, it has all of the primitives for running Python code and sharing objects. Is that what you meant?
Yeah.
You sure?
Yeah. I think, you just showed the example when you run, I don't know, maybe threading. You mentioned that when you stop, there's some special technique that you can, remove or kill the threads, and the resources. And my question was similar to that. If you can.
Yeah. Oh, so can you kill them from the
multiprocessing? Yeah.
Let's process this. Killing can't open file processes. Oh, it's 11 dash. Control C, Control Z. I'm on WSL, so it's Control T. Yes, let's have a look at the API we have on processes. How did we create these? P is the process object. Stopped exit code 0, so that process is no longer running. But you have the PID is one of the attributes on it, and with the PID, and there are nice third-party libraries that let you do operating stuff with a PID. Join kill. Here we explicitly have a kill. Killing processes is much cleaner than killing threads.
Okay. Yeah, thanks.
So it's a real process, and there's a defined. I mean, you can look up how the process is created. It's just a Python process running code that you've given it. Okay, so the last part of this, I love using the multiprocessing module. I've used it a bunch of times. It's great for I/O bound stuff. The memory overhead for processes on a modern system is trivial. So you can run tons of them, particularly if they're I/O bound. But the global interpreter lock is a real problem. All sorts of applications for Python. The Python community has kind of had their head in the sand about it for many years. But finally, in Python 3.13, the GIL is optional. The GIL has been removed, but it's you compile with or without the global interpreter lock, And there's a 5 to 8% slowdown for single-threaded code or code running in a thread for using the optional GILs. They've done a whole ton of stuff. Reference counting is the big problem for Python, and real free threading, because even everything that touches an object increments a reference count. And I explained earlier how an increment is not thread safe. So fundamentally, absolutely every operation that uses reference counting needs locking around it. But we've now got a whole bunch of stuff, deferred reference counting. There are a whole ton more immortal objects which just don't need any reference counting. So a lot of work has gone into it, and it's only 5 to 8% slower. So you definitely shouldn't use it if you're only writing single-threaded code. But as soon as you're using more than one thread, there's an advantage. However, extensions have to be compiled separately against this version. And there's a bunch of caveats. But the PEP 703 is pretty readable, and there's a bunch of discussions around it. So 703. That's not one of the ones I kept open. PEP 703 is pretty interesting. That's already in Python 3.13, which will be coming out soon. Something else that is in Python 3.13 are subinterpreters in the standard library at the Python level. This is the work of Eric Snow. It adds a new interpreters module, but it also provides Python level access to subinterpreters. Now, subinterpreters have been around for donkey's years. They're used by ModPython, the Apache plugin for supporting Python. And this is where you run a bunch of interpreters in a process, but we've never had clean access to them from C or from the Python level. And the advantage of these is that there's what they run within the same process, but you get one GIL per subinterpreter. And similarly, because of problems around shared access, particularly reference counting and who deallocates objects, they have to be deallocated by the same engine that they're allocated. So there were lots of fierce problems. And in the end, we ended up with objects copied between subinterpreters, not shared. So again, it's kind of the actor model. It does impose some limitations on extension modules for being compatible with subinterpreters. And it'll be interesting to see how that works out in practice. But essentially, it gives us a new high-level API for creating a Python engine and executing code in it, and having it be completely isolated from the current interpreter, having its own GIL. So we can typically you would run it in a thread. The exec call is blocking to execute code. So you run that in a thread, and you can have multiple running in multiple threads. That was the C-level work was done for Python 3.12, and in 3.13, it's being exposed in the standard library. So that's, again, another new model for concurrency in Python. So that is all I have for you. Any other questions? Roderick?
Yeah, I was wondering, how would you know which one to use, processes or threads? Or which might be better suited for a task?
I think it would depend on the amount of work. I mean, we have a background task of sending critical email alerts, which we've got a thread pool executor on one touch switch available to us, and we can push tasks onto that. And it would be overkill to use a process for a trivial background task. So I would tend to think, but I would tend to be very careful with threads. There's very limited situations. If you're doing something that's clearly concurrent and you understand what you're doing, and you're confident that the race conditions aren't going to be an issue, I might investigate threads. I wouldn't reach for them. I would try to reach for processes first. But they're a reasonably heavyweight thing, so it would have to really be worthwhile. You know, that'd have to be. Does that in any way clarify?
Yep, thanks.
Yeah, avoid threads. Probably avoid processes as well. Okay, folks. Some of that material was new. I didn't feel as confident as I have at other times, but I still enjoyed doing it. Thanks for turning up. My plan for the next one, particularly aimed at the QA folk, is going to be an introduction level to PyTest. So probably not so helpful for you dev folk. Martin, you might enjoy it. But I will welcome you along to Heckle anyway. And thank you all. See you again soon.
Thank you.
Thank you, Michael.
Cheers.
Cheers,
Michael.
Goodbye.
Thank you.
Bye.
Thank
Cheers,
you.
Michael. Okay.
Bye.
Thanks, Calvin.
See you later then.
Yeah, see you soon.